Hello everyone, I'm Porpin Pungetmongkol from International School of Engineering, Chulalongkorn University, Thailand. Today I'm going to present my poster in IEEE sensor. My poster number is 1018 and here's the topic, smartphone sensor for pesticide monitoring using the copper oxide modified screen printed electrode. So in this work, we are going to deliver a real-time and portable pesticide sensor or pesticide analysis system. So in our system, we need the electrode in order to measure the pesticide. So we're going to measure by using the NFC card reader together with the smartphone that have already been implemented with the application to detect the electrochemical analysis. So we can measure the pesticide as we modify the electrode by using the copper oxide. So whenever there's a presence of the organophosphate pesticide, the oxonate or thionate group of the pesticide will be coordinated with the copper. So in that case, it's going to block the redox reaction of copper, and in turn, it's going to reduce the current of the redox reaction of copper. So we can detect the change in that current and relate it to the concentration of the pesticide by using the chronoamperometry that will be presented onto the smartphone. This is the whole system. So in this work, we are going to modify the screen printed carbon electrode with the copper. So at first, we deposit the copper onto the SPCE using the electrode deposition technique by this recipe. And after we deposit the copper, we can see the reddish color shown in the working electrode. And after that, we are going to anodize those copper surface into the copper oxide nanostructure. And that will change the color into the pale gray colors and shown like in this schematic. If we zoom in into the microscopic view of the electrode, we will find that the copper oxide nanostructure has been fabricated onto the SPCE. The dark area is the SPCE based, carbon based, and the white spot, those are the copper oxide nanomaterials. So those copper oxide will, size nanoparticle will be ranged between 200 and 300 nanometer. So we are going to test the electrical performance of our electrode by using the cyclic voltammetry. So we vary the potential from -1.5 to 0.5 and with a different concentration of pesticide. And we can obtain the calibration curve like shown here in the right panel. So you can see that the calibration curve can be modeled by two linear equations. And in this work, our electrode has the performance and it can be detect the low concentration as low as 6 to 0.7 nanogram per milliliter. That is our LOD. So now we are ready to use the chronoamperometry to detect the change in the current when we apply the higher and higher concentration of pesticide. So we add the pesticide at concentration at every 120 seconds. So you can see that this is the corporate force standard solution. The current is changed and decreased according to the higher concentration of the pesticide. We also test this onto the real vegetable juice. In this case, we select the butterhead lettuce, which use a lot in the salad. So we can see that we also can detect the change in the current as well for this one. And if we compare between the calibration curve of these two solutions, the standard one and the real vegetable juice, the inhibition current of the vegetable juice is lower. That may due to many interference in those butterhead lettuce juice. But anyway, we can deliver the calibration curve and the analysis for both real vegetable and standard solution. That's all for my presentation. Thank you very much.